galaxy populations in clusters. What I mean by unified is we're going to try to get the morphology of galaxies correct as we're modeling them in a larger context. The clusters part is actually going to be preliminary results, but I have results from other contexts which I will be presenting. This is a cast of thousands, particularly computer science help in co-developing. The work I'm going to be talking about today is mostly the work of Michael Tremel, recently graduated student, and other collaborators here. And this is also, the clusters work is in collaboration with Reef, Neil, and Ramil. So, right, if we're modeling galaxies, we need to get these things. And what we see here is the baryonic processes. And so modeling the stars and the gas, even though it's dominated by dark matter, it's that baryonic modeling that we need to get correct if we're going to get the morphology correct. But of course, we don't form individual stars. At some point, we have to have a subgrid model and associated parameters. And so the trade-offs we have is that, right, we need a reasonable piece of the universe because it's the tidal torques that give the galaxy its spin, even though there's no halo morphology spin correlation, you still need the angular momentum, and that comes from roughly 20 megaparsecs away. But we do need the high resolution, so we've mainly been doing zoom-in runs where we focus our resolution on the galaxy, but we still have to, even in kiloparsec, we still need the subgrid model, and these just outline the basics of what we do for star formation, for feedback, and then in my case, I'm using this blast wave formalism to solve this overcooling problem with low resolution that was mentioned earlier. But within this, we have to do some sort of tuning of that subgrid model to match what we see. And this is work by Michael Tremel. We've used this technique called Kriging because we have to search this multi-dimensional space of our subgrid models for ones that match, in this particular case, the stellar mass halo mass relation, the amount of cold gas as a fraction of the stellar mass, the bulge to disk ratio, for example. And each one of these points on this plot represents a few tens of thousands of core hours, right? So we have to run a simulation and see, does it match? And we then search this high dimensional space for optimum points, and we're doing that search across a number of halo masses, and the blue points are sort of best fit models by some measure of closeness to the observed relations. So that's what we're going to start out with, as well as generally matching all these relationships. We get a decent morphologies, and not quite as pretty as the fire simulations, but we have a little trade-off on the resolution. Right, and the trade-off comes because we're trying to model these things in a larger context. Right, so we're going to start with the models I just described based on zoom-in simulations, and then we're going to build up to larger systems. We'd like to do cosmological volumes so we can compare with surveys. We want to see what these galaxies do in groups of clusters. But the universe is big. We don't have infinite computing resource, and so at some point we have to push the envelope both on a resolution and on the volume size we can produce, we can model. Pushing the envelope is a kind way of saying it. Maybe cutting corners might be a crueler way to say it. That we can't quite get as big as we want. We can't quite get down to the resolution we want. But the other thing that helps is having an efficient code. You've seen this slide before. I think the only thing I really want to emphasize, well, let me emphasize that. Thank you again, Ji-Hoon. James has just put out a paper with sort of updated SPH in gasoline, and Chang'e includes that. So essentially, we're bug for bug compatible with the gasoline code, with the advantage that we have that we're able to scale out to 500,000 cores because of the improved scalability. So the first cosmological volume we ran with this code, we refer to it as a Vulcan, and really this is a barely cosmological volume. It's the one justification for this number is it is also approximately the volume of the candles survey, which is what we attempted to match. We only run the simulation to z equal 3. Here we have the mass resolution both in gas and dark. Notice we actually oversample in dark matter, and I'll explain why in a little bit. But the parameters, in some sense, this is no parameters because we set all the parameters with our z equals 0 zoom-ins. Okay, so we take those parameters we got from the zoom-ins and apply it to this volume and see if we can reproduce, for example, the luminosity function of the candles galaxies. And so this is Lauren Anderson's PhD work, where she's looking at the luminosity function in the rest frame UV absolute magnitude, comparing with the candle survey, which is data from Finkelstein in gray. This is various redshifts, and Lauren's galaxies are the colored points. And we're quite pleased to see that we're getting, we really shouldn't be getting the turnoff, well, because we're barely getting L-star galaxies, but we are getting the fade end slope correct, and we're getting the absolute magnitude of the luminosity function correct going out. Here's one discrepancy at z equal 8. But what we learned from this is that it looks like that the mass function continues to rise toward towards fainter galaxies. And this is interesting because notice the slope parameter, when alpha hits -2, that means that most of your stars are in small galaxies, which means most of your photons are coming out of small galaxies. And if you do the accounting of those UV photons, we see that the flux of ionizing photons coming from the small galaxies as a function of redshift from our simulations, that's the dark points, becomes sufficient to keep the universe ionized at about a redshift of 6. All right, so the green line is the flux you need to keep the universe ionized. And so at least in terms of hydrogen ionization, these small galaxies are capable of reionizing the universe and fitting what we know about the ionization state of hydrogen. So that's great, but once we start to look at what happens with higher mass galaxies, we start to run into trouble. So here I have the stellar mass, halo mass relationship, and here's the standard Moster line. And if we only use supernova as our feedback and try to tune the feedback, we get the yellow triangles. And basically, as we try to match these halos of 10 to the 12 solar masses or higher, we're forced to use such a strong feedback that we actually underproduce stars in lower mass halos. And so what we did, and what Michael did to improve this, is to introduce black hole and AGN feedback. So basically, feedback that would help with a higher mass galaxies. And basically, there's three components to his model. We have seed formation in the early universe from low metallicity, very high density gas. Has a probability to form black holes. The black holes then grow from accreting gas, and of course the feedback is the important thing. The other thing is, and this comes to the why we use so many dark matter particles. I think Phil mentioned earlier this week, if you have 10 to the 6 solar mass black holes, two-body interactions could scatter them if you don't make your mass resolution high enough. And even with that, Michael introduced a dynamical friction formula to help the black hole sink to the center of the galaxy and merge. And the power of doing that is that we can actually follow mergers. For this example, we're looking at the star formation rate versus the black hole luminosity in this pair of galaxies that merge. And so we've got a blue galaxy and a blue point and a red point representing the black hole in each galaxy. And we notice that the galaxies merge up here, but the black holes merge several hundred years later. And so we can follow the delay between the galaxy merger and the black hole merger, which will be important for example, gravitational wave experiments. So with that feedback, we ran another cosmological 25 megaparsec volume, same mass parameters and force resolution, but with the AGN feedback that I just described in the last slide. And this one we ran all the way to redshift of 0. Maybe that sort of violates some constitution of running cosmological simulations, but in this volume, we get a range of morphologies from low star forming rate to high star forming, compact objects versus dispersed objects. And if we look at how they fall on this stellar mass halo mass relationship, we get actually quite a good agreement at the high mass end, all the way up to group scale, 10 to the 13 solar mass halos. So we're quite pleased with that. Furthermore, looking into the black holes, we're matching the black hole mass stellar mass relationship at the high end, and of course this scatter is also a scatter that's seen in the observation. So we're quite happy seeing a scatter in the black hole mass stellar mass relationship at these low masses. Okay, so I promised to talk about clusters. Here's the usual stuff about clusters. I think the important thing for us simulators is that in clusters we do see the baryons in X-ray and in the Zanyaev-Seldovich effect. And in terms of feedback models, right, in an isolated galaxy, I can do whatever we want with feedback and throw the gas out into the IGM where nobody sees it. In a cluster, that becomes the intercluster medium, and of course, that becomes an observable. So we get a new constraint on our galactic feedback. But clusters have a challenge. Okay, as well as, right, we need the feedback in the individual galaxies, which I talked about. This work has been actually stalled for quite a while because, right, our hydrodynamic methods have to model two-phase media, and that was a problem for a while. And you just got this huge range of mass resolution if you want to model, say, a coma-size cluster. And furthermore, as you model it, all the computation You know, in term, here I'm talking about on a parallel machine, all the computation is concentrated spatially, and somehow you have to divide that across thousands, tens of thousands of processors, making load balancing quite difficult. Nevertheless, we gave it a go. We call it Romulus C. Romulus because, again, we have the same AGN and star formation models as the previous simulation, but here we just picked the highest mass halo in a 50 megaparsec volume. It turns out to be, thank you, about 1.5 times 10 to the 14 solar masses, which we run in as a zoom in with the same mass resolution. How did it do? Again, this is sort of, we're just opening the box here to see whether we did reasonably. Here is the spectroscopic emission weighted temperature as a function of halo mass. The lines here are from observations. Here's a few other simulations. I took this out of a simulation paper by Liang et al. And here's our zoom-in simulation. So it's a little bit cool for its mass, but a little more promising is that if we look at the entropy, so this is the entropy here within M500 and within M2500 as a function of the X-ray temperature, and particularly the central entropy seems to fit nicely with observations. Right, my previous attempts to running clusters, I tend to get lumps of cold gas, a large amount of cold gas in the center of the cluster, and we don't seem to be getting that. So we're quite pleased with that. The stellar mass halo mass relationship, here's our cluster at again a few times 10 to the 14. The stellar mass is just under 10 to the 12, and it fits nicely on Andre's stellar mass halo mass relationship, which I should point out was where he focused on clusters in deriving that relationship. There's this issue, and so what's going on here? Well, these are not field galaxies, and if you remember from Farad's talk, there was a great scatter in the stellar mass halo mass relationship for her satellite galaxies, and here our galaxies are now satellites in this cluster, and so what's probably going on here is that the dark matter is being stripped by interactions with the cluster. And to look at that a little bit, we divided those satellite galaxies into two classes. The red are central, that is, their distance from the central galaxy is less than a fifth the virial radius, and the blue is galaxies that are within 1/5 of the virial radius, so the very outskirts of the galaxy. And we notice that the galaxies in the outskirts fit nicely on the stellar mass, or the observed stellar mass halo mass relationship, and it's the ones interior that are boosted. Presumably, this isn't the stellar mass going up, this is the dark matter mass going down because of interactions with the cluster. The central, we do have a BCG. I don't know too much about it, except I told you it's stellar mass and its morphology. It is a little disturbed because it just had an encounter with another satellite galaxy. I mentioned the gas. Here's the plot of the gas temperature. So this is 1 megaparsec in radius, and so this is roughly the virial radius out here. Again, interesting cold gas, relatively cold gas out here, but the central part is mostly hot gas. And again, the way I've done the plotting is that the coldest gas shines through, right? That's the way I did the plotting. So it's clear There's a little satellite galaxy in here, but the center is nicely filled with hot gas. So, first takeaway, we can do these with sufficient computing power, can do these simulations where we both are modeling the galaxies and the cluster as a whole using the same parameters that we use for the field galaxies, and getting reasonable results for the stellar mass, the intracluster medium, and the galaxy morphology within the cluster. And so this is good because, you know, there's all kinds of things we can now do with these cluster models. I've mentioned a few here. This is particularly interesting with the LSST coming up. But I think that I mentioned this before. A very interesting thing is I told you that the models, right, you're not laughing at me for these models. I haven't made any obvious mistakes in doing the cluster, the galaxy cluster, but I may have made some unobvious mistakes. Right? If we don't fit the cluster, then maybe we learn either something new about our feedback models, or perhaps we learn something new about cold dark matter. In any case, there's new stuff to be learned here. And so thank you. Aye.
I would think that the listing that we found in the responses would be a very powerful.
Yeah, yeah. I have not. I mean, metals get out into the ICM. So qualitatively, I've got metals. I can't. I haven't done the analysis yet. Like I say, I've just opened the box on these things. Yeah.
Strong feedback, high load mass load factors, or medium or low? I don't know the theory. So.
Anybody? I don't know how to classify my own. So it's pretty. I mean, it's so it's basic. This blast wave feedback model. You know, you shut off cooling for a little bit to prevent overcooling.
Ones, twos, and threes, or fives and tens.
It's I would say it's probably on the lower end. Yeah. Yeah. Yes. So Phil Chang wrote basically ported you know, Aripo's algorithms to the Changa framework. That's available for download. I actually don't. I mean, I helped him out a little bit with it, but I really haven't run anything with it. But you're welcome to try. All right, so Anna. Oh. Yes. Here. Oh yeah. Oh yeah. This one. Yeah. Mm-hmm. Okay, so the observers don't see these, is what you're saying. Yeah. Okay. Certainly not in the Romulus simulation. I mean, we tuned the black hole feedback and the supernova feedback see, together, right? Although, I mean, right, to make it a little more efficient, we first got the supernova feedback tuned onto the low mass galaxy, and then did some tweaking, right? Basically narrowed the number of simulation, the dimensionality of our parameter space when we added the black holes. So we might have missed something by doing that. And that would be the kind of thing we would have missed.
So we should stop here. We have time for the discussion. So,
all right. Okay.
Sorry.
Anatoly was bugging me for a while.
It's all amazing how the heck it could possibly do anything.
How
the heck it could possibly do anything reasonable, but it does. Right? So
I agree. I'm surprised. Yes. Yeah.
So you don't do that, but instead you do no fully radiated
Yeah.
plus AG.
Right.
How much do you spend on it?
Oh, yeah. I mean, Ji-Hoon said we're not supposed to, that's a secret. No, no. Yeah, so we're talking a couple 100,000 core months. Yeah. Is that? Yeah, so, basically I was running on the machine at 32,000 cores. Yeah, it took a while.
Okay.
I think now we are done.
Sure.
So thanks.